Good morning, guys. Today we're going to look at a couple specific types of random variables. So we've talked about what random variables are. We have talked about how to transform random variables. Now I'll look at a couple special cases of random variables, particularly binomial random variables, because they're going to help us later on with a lot of our inferential statistics. So the two special random variables we have are binomial and geometric. So what is a binomial random variable? That's what this first part's going to deal with. So here's our problem. Bill's an 80% free throw shooter. The number of shots that he will make tonight out of 7 attempts is a specific type of random variable called a binomial random variable. Now, why is it random? Well, I don't know how it's truly random, but if we're just looking at a specific, we are randomly selecting a specific attempt, there's an outcome related to it. So 80% free throw shooter, shooting 7, how many shots is he going to make? So this would be a discrete random variable. All right, there's a finite number of outcomes that we could get from him shooting 7 attempts. Plus we actually have kind of another chance process on does he make it, does he not? So it's kind of multiple things we're looking at. How many things happen out of the 7, but how many, or what is the actual outcome from a single event or a single trial? So this meets what we can call the binomial setting. Binomial setting means we've met these 4 conditions. So first off, it needs to be binary. What does binary mean? Binary means only 2 outcomes are possible. We have only 2 outcomes possible for a single trial. Or in this case, attempt. So do we have 2 outcomes possible? Yeah. He's either going to make or miss. So make or miss are the only 2 possible outcomes for a single attempt, or a single free throw. We're going to throw out the possibility of lane violations. We're going to get a little loose with kind of our understanding of free throw attempts and stuff right here. Just so we have a good example to work through the math on. All right, so first off, it's got to be binary. Second off, it's got to be independent. What does it mean for the trials to be independent? So the outcome of one trial does not affect other trials. Does not affect. So whether or not he makes this shot, one shot, has no effect on whether or not he makes other shots. So make or miss one free throw has no impact on whether he makes or misses other free throws. All right, so again, this is where I said we're going to kind of get loose with our idea of what a free throw is. We know reasonably that if he missed a shot short last time, maybe he comes in, tries to put a little more on it the next time. But hopefully his muscle memory, he's done it so many times, is really what's taken over, and he's not thinking. He's just trying to go up and react. But again, there's always a little bit of play there. But in general, just because he missed the first one doesn't mean that he's more or less likely to miss the second one. That's what we're talking about. It's not changing the probability. Number. What do we mean by number? There needs to be a fixed number of trials. Okay? Fixed number of possible outcomes. A fixed number of trials. So this is not a situation where we're like, just keep trying until you make it. Right? That wouldn't be a binomial setting problem. That's something we're going to talk about in part 2 of this lesson. So fixed number of trials. So do we have a fixed number of trials? Yeah, he's only making 7 attempts. And last one is success. And this is the big one. It kind of works off of independent. This is really what we need. We've got to have this idea of a constant rate of success, and because it's independent, it should lead us to that. But it's the probability of success is constant for every trial. The probability of success is constant for every trial. So do we have that? Yeah, we do have a relatively constant probability of success. What's the probability of success on a single attempt? 80%, because he's an 80% free throw shooter. So that's the way you want to think of it. So we can say historically, Bill is an 80% free throw shooter. So we believe that he has an 80% chance of making any free throw. So this is how we determine if something is a binomial setting. So it's very, very important because it's going to kind of dictate what type of calculations we're able to go through. So this idea that you have a certain number of trials, you want a certain number of successes out of those trials, and every single trial has the same probability of being successful out of a yes or no situation. So the mnemonic that we use, or the acronym that we use, is BINS. Binary, independent, number, and successes. Yes or no outcome. One trial does not affect the next. We are only trying it a certain number of times, and every trial has the same probability of success. If we've hit all 4 of those conditions, then we are dealing with a binomial setting, a binomial situation. And once it's binomial, it's really, really nice because we have a set formula for that. And so when we have these types of problems, we can actually calculate these binomial probabilities. Now, that's the random variable part, how many shots he makes. Now let's look at the probability that he makes certain number of shots, okay? So let's just kind of say that probability of getting 2 shots, something like that. So we've got a couple ways we can do it. One, we can calculate by hand. Another, we can use technology to calculate. So let's talk about the by hand, just so we understand what it is that we're talking about here. So we've got this weirdo formula up here that I've got binomial coefficients and exclamation points and all types of craziness. So what am I saying when I say he makes exactly 2 out of 7 shots? Exactly 2 out of 7 shots. Well, that means that, for example, he makes the first shot, makes the second shot, and then misses, 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 misses. Well, what was the connecting word I used? And. Make, and then miss, and then miss, and then miss, and then miss, and then miss. Well, we know by our general multiplication rule, when we see or hear the word and, that's a multiplication problem. So really what I'm doing is making it 2 times. So taking the probability of 2 makes and then multiplying that by the probability of my 5 misses. So that's what this little formula right here says. So this P and this K, what does P and this K represent? Well, P is just the probability of success. Probability of success. That's probably that he makes a shot. K is the number of successes. So he's an 80% free throw shooter, so there's an 80% chance that he makes it, and we need him to do that twice. So we do 0.80 times 0.80. That's for the 2 makes that he has. Well, what's this other stuff stand for? Well, if P is probability of success, by complement rule, 1 minus P is probability of not success. Well, what do we call not success? Failure. So P is probability of success, 1 minus P is probability of failure. Probability of failure. and then n minus k. What is n? N is our number of trials. Okay? So n is number of trials. I'll talk about this guy on the front here in a minute. K was number of successes. So if I take my trials, my attempts, minus my successes, what am I left with? How many times I failed. So this is just the number of failures. So this whole little crazy looking formula comes down to, what's the chance of me succeeding and how many times did I do it? What's the chance of me failing and how many times did I do it? So 80% free throw shooter, and we need him to succeed 2 times, so that's 0.8 raised to the second power. And then the other 5 times, which occur 20% of the time, he misses 20% of the time, we need that to occur 5 times. So you would do 0.8 raised to the second, 0.2 raised to the 5th power. So that's what that part of the formula means. But here's where it gets a little bit trickier. What if he didn't make the first shot and the second shot and then missed 5? Couldn't he have made the first, missed the second, made the third, missed the 4th, 5th, 6th, 7th, or made the first, missed the second, missed the third, made it on the 4th, missed 5, 6, 7, or missed the first, made the second, made the third, missed the 4, 5, 6. Right? There's a lot of different ways we can get to making it 2 times. Well, what was that word I was using to connect each of those options? It was or. And we know that or tells us to do what? With probability. We add. So what I would realistically do is take this 0.8 times, take my 2 successes times my 5 failures, and rearrange them all the different ways I could get, and take all of those products of 7 trials and add all of those together. That's what this guy right here on the front is. That's our binomial coefficient. So the binomial coefficient calculates all the ways to get, in this case, k successes, or 2 successes, out of n trials. Okay? So this right here is going to tell me how many different ways, because I don't need to actually take 0.8 times 0.2 times 0.8 times 0.2222, and then 0.8 times 0.2, 0.2, 0.2, 0.8, 0.2. I don't have to multiply them in those specific orders. Multiplication is commutative. I know I'm going to have 2 successes, I'm going to have 5 failures. I just need to know how many different ways we could rearrange those and then add all of those together. So I need to know all the different ways to get 2 successes out of 7 attempts, or k successes out of n trials. So that's what this formula does. So there's a couple ways we can write it. You may see it like this, n over k, in parentheses, looks like a fraction with no fraction bar. That's kind of an older way of writing it, but some texts use that. Some tests use that. You'll get college professors that still write it in that way. So n over k, that's just saying number of trials, number of successes. Now this is what we usually, or you probably will more commonly see it, in ck, and there's probably other ways that people are writing it these days that you may come across. So in ck, so what we think of that is, I want 7 trials chosen 2 at a time, right? Okay, or 7 possible successes chosen 2 at a time. So in ck, this is the actual formula. These are just notations to get us to this formula. So what does that formula mean? Well, first off, there's something really interesting in this formula that we've talked about a little bit in this course, kind of just with conversations in class, but you may not have seen it in prior math classes. And it's this guy right here. Now that is an exclamation point. But in math, it doesn't mean excited. That does not mean that this n is really excited to do some math, and this k is really excited to divide it into that really excited. That's not what an exclamation point means in math. In math, that's a factorial symbol. Okay? Factorial. Keyword being factor, right? Factor means multiplication. So factorial just means multiply from that number down to 1. So if I had, from that number down to 1. So say that I had 6 factorial. It means multiply from 6 all the way down to 1. 6 times 5 times 4 times 3 times 2 times 1. If I had 10 factorial, 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. 100 factorial. 100 times 99 times 98 and 99 or 97, all the way down to 1. That's what it means. Now, are we going to have to actually do that? No, because when we're using them, see how there's fractions? Well, when you have fractions and everybody's going down to 1, you'll notice a lot of those factors are in common. They'll overlap at some point, so things will cancel out and make the math and calculations easy. Let's go ahead and let's do this. So let's do that example of 2 makes out of 7 attempts. All right, so if I'm going through here, so that's 2C7. So 7 trials, 2 successes, or we could say 7C2, 7 trials, 2 successes. We can go 7 factorial over 2 factorial times 7 minus 2 factorial. And you'll take you'll definitely take some math courses later on where they'll kind of develop where that formula comes from. We don't really get into counting methods and stuff like that in this course. So you can look up some combinatorics courses or classes and stuff, and you'll be able to see where that comes from. Or if we get some time in class one day, we can talk about it, and I can show you where that comes from. But going through and doing the math on it. So 7 factorial, that's 7 times 6 times 5 times 4 times 3 times 2 times 1. I don't want to multiply that out. Let's keep working. 2 factorial. 2 times 1. 7 minus 2 is 5. 5 factorial is 5 times 4 times 3 times 2 times 1. So what do we notice about all this? Well, look, 5, 4, 3, 2, 1, 5, 4, 3, 2, 1. So all that stuff cancels, and I'm really just left with 7 times 6 over 2 times 1. So that's 21. So that means there are 21 different orders or different ways that he could make 2 shots and miss 5. Okay? So the different location of those makes and misses rearranges, there's 21 of them. So if we were going to go through and do the calculation here, I said there's 21 different ways that he can 0.8 raised to the second, that's make 2 misses, and 0.2 raised to the fifth. Make 2 attempts or miss 5 attempts, and miss 5 attempts. So that's the by hand way that we can do it. Next, let's go over and let's look at how we can do this on the calculator a whole lot faster. So you will need your TI-84s out for that. So on the calculator, we've actually done a little bit. We've worked in this menu before. You're going to hit second vars. That's your distribution menu. It's the same place we went and looked for normal distributions and our inverse normal function. So same menu, we're just going to move to binomial distributions. And then later on in part 2, we'll talk geometric distributions. So if I want the probability of making exactly a certain amount, so I want the probability that x equals k, or in this case, probability that our number of successes, x is our number of makes, is exactly 2, I would hit second vars, go all the way down to option A, and I'd go to binomial PDF. Now, I know you're saying, well, you told us with normal distributions, never pick PDF. Well, with normal distributions, we didn't want PDF, because normal distributions, we don't want it exactly one outcome. We wanted to know a range of outcomes. Okay? This, I want to know the probability of getting an exact success. So I want to know the height at one specific value. So I will use PDF when it's an equal sign. Okay, so when I'm looking for an exact value, exact number of successes, then I will use PDF. Now, when I'm looking for an inequality, more than, less than, greater than, then we're going to come in and we're going to use CDF. We'll talk about that one in a minute. But if I'm looking for an inequality number of values, I want to know at least 5 or less than 3 or more than 2, something like that. That's when you're going to use the CDF function. So when it's inequalities, we'll use CDF for cumulative density function. And when it's an exact or it equals a certain number of successes, then we're going to use probability density function, PDF. So go to binomial PDF, and then it's going to ask you for, if you got the older calculator, you're going to type it NPK in that order. N is number of trials. P is probability of success. And K is number of successes. NPK. In the newer calculators, it'll say trial, I think it says trials, probability, and X. So trials is going to be obviously your number of trials, so 7 attempts. Your probability, your P is going to be 0.8, and then your X is going to be number of successes in this case, which would be 2 if we were talking about the problem example we just looked at. All right, so that's how we can get the exact same thing on the calculator that we got from this big old beautiful formula. So let's go through and let's actually do some calculations. We've got, we'll start with number 2 actually, let's practice one. So let's not start at part 1, let's go number 2. What's the probability that Bill makes exactly 4 of his 7 attempts? Probability that Bill makes exactly 4 of his 7 attempts. So we're looking at probability that X, because X is our random variable, right? The number of shots he could make is equal to 4 out of 7. So we could do that as our formula, right? We could do NCR, so I could do 7C4 times the probability of success, 0.8 raised to the 4 successes, probability of failure, 0.2 raised to the 3 failures. We could go through it that way. Or we can go to the calculator and we can do second vars, okay? Go down in your distribution menu and we're going to go find option A, which is binomial PDF, because it's an equals problem. I want 7 trials. I want it to be 80% successful, and I want that to happen 4 times. So take a minute, go to your calculator, key this in. Okay, so second vars, which is your distribution menu, and go down to option A. Okay, go down to option A. Binomial PDF, 7.8 and 4. So take a second, pause the video right here, and go calculate that for me. All right. So when you did that, you should have got 0.115. So what's that mean? That means that if he makes 7 attempts tonight, there's about a 12% chance that he makes exactly 4 of them. Okay? If he makes 7 attempts tonight, there's about a 12% chance that he makes exactly 4. Or we could think of it, out of all the times that he does sets of 7 attempts. Okay? So out of every time that he does a chunk of 7 attempts, about 12% of those result in him having 4 successes out of those 7 attempts. So we can kind of think of it as what's coming up tonight, or we can think of it as kind of a long run probability type thing. All right, so let's step up here back to question 1 then. So question 1, now that we know how to calculate for a specific number of outcomes or successes, write and sketch a histogram of the probability distribution for the number of shots that Bill makes in his 7 attempts. So before you do calculations, we need to list our sample space. So define our random variable. So X is the number of makes out of 7 attempts. So what are the possible number of makes he could make? Or he could get? Well, we know the most he could get is 7. What's the fewest number of shots he could make? Not 1, 0. He could make 0 shots. So there is a possibility, so there is a probability of making 0 attempts. Now he's an 80% free throw shooter, so common sense says it shouldn't be a very large probability, but there is a probability. So he could make 0, 1, 2, 3, 4, 5, 6, or 7. So what I want you to do is, just like we did here, we've already got the 4, 0.115. So we know the probability makes exactly 4. I want you to repeat that process and calculate for each of those possible outcomes. So you're going to run your binomial PDF 7 more times. So I'll pause the video right here, and I'll let you guys do those calculations. All right, and hopefully you got these probabilities. All right, so as we can see, very, very low probability that he makes 0 shots, and his highest probabilities were up here around 5, 6, 7 shots. Now, why did none of these equal 80%? Well, because it's not the probability that he makes a certain number of shots. It's one shot is 80%, and we're looking for how all those shots could be distributed. Now, we do keep in mind that what we learned back with random variables or probability distributions of random variables, all of this stuff right here should have to be 100% of his possible outcomes. So I want you guys now to take this probability distribution and turn it into a histogram for me. And I'll pause right here and wait for you guys to do that. All right, you should have got this. So there is our histogram. So probabilities going from 0 to about 36.36. Lists our number of shots made, 0, 1, 2, 3, 4, 5, 6, 7. And we see the peak is over here on the right. Now that should be an intuitive thing for us, that his most likely outcomes, the highest probability of something happening, is that he's going to make 5, 6, or 7 shots. There's almost no chance, it's a very, very tiny chance, almost no chance that he makes 0, 1, 2, or 3 shots. And by the time you get to 3 makes only, there's only about a 3% chance of that happening. So he's most likely to make 5, 6, 7 shots. Well, why is that? Well, the reason he's most likely to make that is because he makes 80% of his shots, right? So it should be kind of, I think, an intuitive thing for us there. So let's go through and use this table to get a couple more calculations. So let's look at the probability that he makes less than 4 of his 7 attempts. So probability of less than 4. So probability that X is less than 4 out of 7. So that's an inequality. So that means there's multiple ways we could do that one. Now, we could use our formulas right here, but we're going to come and talk about them in a minute. I want to go through, I want to just do this one using the table. What does it mean to be less than 4? Well, it means that we could be 0 or 1 or 2 or 3, right? Those are all the different ways that he can get less than 4 makes. Well, we know that OR means what? Well, OR means add, right? So the way that we would get this is we would find the probability of 0, 1 makes, plus 1 make, plus 2 makes, plus 3 makes, and just add them together. Well, we have those already. So 0.000128, 0.00035, 0.004, and 0.028. So when we do the calculation on all that, we get, what's that add up to give us? 0.324. So there's just barely over 3% chance that he makes fewer than 4 shots. Okay, about a little over 3% of a chance he makes fewer than 4 shots. Now we could again do that using the binomial CDF on the calculator. Now I want to take a second and talk through that. I've got 4 different possible scenarios here using these, and it's all because CDF, as with most of our calculator, our density function stuff, it's a less than or equal to calculator option. So when we type binomial CDF in and we say a certain number of successes, it reads it as, okay, you're getting less than or equal to that number. So that's why when we have a less than or equal to situation, it's just normal binomial CDF. If we have anything other than that, not an at most, but an at least, or a less than, or more than, we've got to adjust. So how do we adjust? If I had less than 4, like we did right here, I'm not going to type 4 in, because it's going to read 7 trials times 80% probability times, 80% probability times, at 4. It's going to read that as 4, 3, 2, 1, or 0. But I don't want that if I want less than 4. I want 3, 2, 1, 0. So the way we adjust, because binomials are going to be countable and discrete and finite, we just subtract 1. So less than 4 is the same thing as less than or equal to 3. So I'm just going to take one number off my number of successes. So that's what that right there means. Binomial CDF with 7 trials, 0.8 success rate, and 3 or fewer successes. So CDF means this number or fewer. Well, what if I'd said I want more than a certain number? So this situation right here. So I want more than 4 successes. Well, more than is not less than or equal to, correct? And not means subtract it from 1. That's our complement rule. So if I want more than 4, then I don't want less than or equal to 4. More than 4 means 5 or 6 or 7. That means I don't want 4, 3, 2, 1, 0. So I want 1 minus the CDF of that value. So when you have a greater than situation, you're going to use CDF, but you're going to use 1 minus. And what if I want a greater than or equal to situation? So if I want at least 4 makes, or greater than or equal to 4 shots. Well, if I want greater than or equal to 4 shots, I don't want 3 or fewer shots. And you always have to count it as an or equal. Remember, CDF is a by default a less than or equal to function. So you always have to think of it in those terms. So if I want greater than or equal to 4, I don't want less than or equal to 3. So don't want means 1 minus, and then I take my 4 and subtract 1 and turn it into a 3. So you can kind of reason through each one of those. Now, some of the newer calculators have the newest operating systems, and they're nice, and they'll ask you like the inequality. But the older ones, they don't have that, so you've still got to type the NPK, and you've got to adjust. Remember, if it's greater than, it's a 1 minus situation. Okay? And if it's less than, we use K minus 1. If it's greater than or equal to, we're going to use K minus 1. But just keep in mind that CDF, binomial CDF, is a less than or equal to function. So if you will think of it as a less than or equal to function, you can key anything in just by adjusting either the K or subtracting the whole thing from 1. All right, so that's how we could use the calculator to do this exact same problem. Okay, so less than 4, so I would do binomial CDF for 3. Now, what if I wanted at least 1 free throw? Okay, so at least 1 free throw means what? So probability of at least 1 means I could have 1 or 2 or 3, all the way up to, or just means add, all the way up to 7. Now that means I'm having to calculate 7 different probabilities right here. Or I can do the complement, right? Because at least 1 means not 0. 1, 2, 3, 4, 5, 6, 7 means not, it means everything except 0. So I could just think of it as 1 minus the probability of making 0 attempts, which is a lot easier to calculate one thing. And that's actually what we would be doing in an at least a greater than or equal to situation using the calculator. So 1 minus the probability of 0, well, we know by our table the probability of 0 is 0.0000128. So when we subtract that out, we're going to get 0.990999872. So there is almost a 99% or an over 99% chance that if he's an 80% free throw shooter, he's going to make at least 1 out of the 7 attempts. Very, very likely thing to occur. So that's how we can do calculations with binomials. So the key is recognizing. So that's how we can do calculations with binomials. The key is recognizing that it is binomial, and then getting the calculator instructions, or if you want to do the formula, get that stuff correct. All right, now let's talk about why, some characteristics of binomial are very important and how they can help us kind of going forward with our inferential statistics we've got coming up. So a binomial random variable, if it's a random variable, we know the binomial is going to be discrete in this case. If it's a random variable, then it should have a mean and a standard deviation. It's quantitative. So what do we do that mean and standard deviation? Or how do we get that mean and standard deviation? Well, mean just means expected value. So just think of this from a common sense standpoint. Expected value. What do we expect to happen? Bill takes 7 shots. Bill's an 80% free throw shooter. How many do we expect Bill to make? Well, if he's an 80% free throw shooter, we expect him to make 80% of his shots. So whatever 80% of 7 is would be the expected value. Well, that's what mean is. That's what we talked about with random variables. Mean of a random variable is just the expected value. So the expected value is what we expect to happen. So N is the number of trials, P is the probability of success. So 7 attempts, 80% free throw shooter. So we expect Bill to make 5.7 shots. We expect him to have 5.6 makes, not 5.7 makes. Right, that's it. That's all you need to understand right there for mean of a binomial random variable. Take the probability of success, multiply times how many he's trying. And that's how many times we would expect him to be successful. So what does this mean? This means out of many sets of 7 attempts, we expect Bill to make 5.6 shots on average. That's what the expected value means. Okay, so don't overcomplicate that, okay? Now the standard deviation of our binomial random variable is a little bit more complicated about how we come up with this formula. It's, I think, a fairly simple formula to remember, but it is a little more complicated. Not terribly important for what we do to understand where it comes from, but if we can get some time in class one day, we can draw out and write up kind of where this formula comes from. But what you can see is it's really taken your number of trials times P. P is probability of success. And what's 1 minus P? Probability of failure. So it's almost like taking your expected value times your probability of failure and square root and all that stuff. So for us, the standard deviation would be 7 attempts times 80% successful, 20% failure. 7 attempts times 80% successful, 20% failure, and we get 1.05. Now it still means the same thing that all standard deviations mean. So it means out of many sets of 7 attempts, we would expect the number that he makes to typically differ from 5.6 by about 1.05 shots. So the typical number of shots that he makes, or the number of shots that he makes out of every set of 7 attempts, will typically vary from the expected value by 1.05 shots. So that's our mean, that's our standard deviation. We need to get these locked in right now because what we're going to see later on is that this is a very important value when it comes to doing inferential statistics with proportions, because a proportion is a binomial, right? Something is this or it isn't. We're counting it in this group or we're not counting it in that group. So binomial, all this binomial probability stuff is really just setting up for us to be able to work with categorical data, with things that we calculate through proportions. So it's kind of a way we take categorical data and turn it into quantitative data by thinking of it as binomials. So mean and standard deviation. Last thing we'll talk about is a couple of conditions. When can we use certain characteristics? So first, binomial sampling, 10% condition. When taking a simple random sample from a population, we can use a binomial distribution to count the number of successes as long as our sample size is less than or equal to 10% of our population. We don't want to be too big, and we'll talk later on about why we kind of have this cap of 10%. But we don't want our sample to be too big, because then what we start getting into is, what did binomials say? Binomials said we needed to be binary and we needed to be independent. So for us to feel real good, like we talked similar in the transformations unit, or transformations lesson that we did the other day, we need that independence between the groups so we can get in and start doing some of these calculations, like combining standard deviations and things like that, or calculating these standard deviations. So this 10% condition kind of helps us to keep that independence, but we'll talk more about that when we get into talking about how to use this stuff from a proportion standpoint. So big thing we need to get right now is I can treat it like binomials if we've met that 10% condition. And then this next one makes it even better, because what it does is it takes that binomial, which is nice and clean and stuff, but we can actually turn that binomial into a normal. So tomorrow, you'll see on your note-taking guide, I've got a couple little pictures right there, and we'll talk about this last condition a little bit more in depth. But that's called the large count condition. And you'll need to know these, because we're going to reference these from probably here on out for the rest of the course. 10% condition and large counts condition. So large counts condition says if n, that's your sample size, if your sample size is large, we can actually use a normal distribution to estimate the probabilities. Okay? If our sample set is large, we can use a normal distribution. So what do we notice about Bill's graph over here? We noticed that there was a very little chance of this stuff happening and most of this other stuff happening. Well, what's going to happen is, if I was trying 10 shots, or I tried 20 shots, or I tried 100 shots, what would happen is that this little tail becomes even smaller and smaller and smaller, and we end up just with this section right here, which the larger we get, the more it takes on this normal distribution shape. So then we don't have to work with binomial calculations off the calculator, or the binomial formula over there. We can actually work with all of our normal distribution things. We can take it and make it more of a continuous type deal. So large counts condition. If the sample is large, or the number of trials is large enough, we can use a normal distribution to estimate the probabilities. Well, how large is large enough? Well, this is a rule that you're going to need to get right now. Large enough means NP is greater than 10, and n times 1 minus p is greater than or equal to 10. What the heck does that mean? Well, let's n times p. Where have we seen that before? I don't know, right here, maybe at the expected value. So what this is the expected successes are greater than or equal to 10. So we would need to have at least 10 expected successes. And then if n times p is expected successes, well, what's 1 minus p? 1 minus complement rule, right, means not P, not success. We call not successes as failures. So expected failures. So the expected number of failures also needs to be greater than or equal to 10. When that happens, the distribution takes on a shape that looks so much like a normal distribution, we can just use normal approximations instead of binomial approximations. And what you'll see is for those large data sets, whether you work it as a normal, whether you work it as a binomial, your answers are going to be so close together, it doesn't really matter which one you use. Now in this one, could we use a normal probability for it, or normal distributions to calculate? Well, what was our expected value? Our expected successes was 5.6, so our expected failures would have been 1.4 misses. So expect them to make 5.6 on average, we expect them to miss 1.4 on average. That's not 10 and 10. So we'd have to get much higher to get up to that 10 level. So if we got to say 50 shots, okay, so for 50 shots, 50 times 0.8 is 40, right? So if he's making 50 attempts, we would expect 40 of them to make and 10 of them to miss. That, now we've met that 10 condition, that minimum of 10, that large counts condition on both pieces. All right, so that's kind of the minimum that you would need to have, at least 50 to be able to use a normal approximation. Anything less than that in this situation, because of the probabilities, would need to keep using your binomials. All right, so that's it for part 1 of this lesson. So we're going to look at in the next video about geometric distributions, very similar to binomial distributions or binomial random variables. But geometric random variables kind of take that question of how many shots will he make out of a certain number of trials and kind of flips it a little bit. So jump over and we will now talk about in part 2 geometric random variables.